Today we're looking at the first lesson of the new unit, congruent triangles. We've talked about triangles already, but today, this unit we're going to deal with congruent triangles, how to prove triangles congruent and segments congruent from congruent triangles. But before we do that, we're going to begin by looking at what congruence is and how transformations relate to congruency. Filling in our definitions from our notes, we have two figures are congruent if they have the same, and you'll recall this, size and shape. You recall that we use those terms when talking about transformations, and you'll specifically remember rigid motion. The more formal definition, more formally, two plane figures are congruent. By two plane figures, they mean two figures. If and only if one can be obtained from the other by, and this is where that rigid motion came in place. And if you recall, rigid motion was when we moved a shape and we transformed it either through translation, reflection, or rotation, and if it kept its size and shape, then we said that it had rigid motion. Which basically all we're saying now is that if it has rigid motion, it's congruent. So what all this means is if I've got two shapes, suppose I have a triangle like this and another one like this. And we'll just, for now, I know they're not exactly the same, so they're not, but we'll just say they're congruent. To get this shape to look like this shape, we would have to first flip it so that it would look like that, and then we would have to translate it and move it down. And if we were to do that, it would maintain its same shape and it would map the other figure. So this figure would be congruent to this one, and we can get it to map it by a series of transformations, be it rotations, reflections, translations, and so on. Okay? So, next we have two triangles. Use the definition of congruence in terms of rigid motion to describe whether the two figures are congruent and explain your answer. Well, looking at these two triangles, they are not the same size and shape. They have different sizes. Since rigid motion preserves distance, meaning that the distance from point A to point B is different than D to E, and if it did have rigid motion, it would have the same distance. That means there is no rigid motion between these two triangles, therefore they are not congruent. And the way we would write that is to say that triangle ABC is not congruent to triangle DEF. Notice that right there is the symbol. It's the equal sign, the congruent symbol, with a line drawn through it. Not congruent. Okay, and now we have another example. We have this shape, and you'll notice that they are congruent to each other. You can map, notice they put 4 letters. It's a 4-sided figure, so we have 4 corners or 4 vertices. So we use 4 letters. By the translation, it has the following coordinate notation. Now, coordinate notation is when we're talking about this right here, the vector. Basically, what is happening to J to get to P, this new place? You remember that we would count the horizontal change first, which moves to the right, so that would be positive 5. And then the vertical change, which would be up 3, that would be positive 3. Had it been to the left, we would have said negative. Had it been down, we would have said negative as well. So you'll notice that each of these vertices is translated to the right 5 and up 3, from K to Q, from L to R. So because of this, This translation has rigid motion. It maintains its shape and size. Therefore, we would say that JKLM is congruent to PQRS. Okay, let's look at, that's all the notes that we have in your notes packet. Let's look at the actual assignment now. Okay, looking at this first one, we are talking about, we're going to determine whether they're congruent or not. Number one, those two triangles, are they congruent? Well, yes, they have the same size and shape. So we're going to say yes, they are. Now, what type of transformation occurs to get from this triangle to this triangle? Well, that would be reflection. It actually would be reflection across the y-axis. We don't have to write that, but just to see that, yes, it's reflected across this point, this line right here. Looking at number 2, we have two figures that do not have the same size or shape. So my answer is, are they congruent? We're saying no, they're not. The reason they're not is there is no rigid motion. As one changed to the other, the figure did not maintain its size or shape, therefore it has no rigid motion. I'll let you do number 3 on your own. Let's look at number 4. Okay, what we're looking at here is we're saying we have a pre-image, which is drawn. That triangle is the pre-image. We're going to write the image, and we're going to start with point A. Notice that we're going to change the x and y. We're going to subtract 2 from the x coordinate and then add 3 to the y. So if we're doing y, we're looking at this point right here. So -1 minus 2 equals -3. -3 plus 3 is 0. So my image of A would be -3, 0, which would be right there. Okay, now we'll do B. We're going to take we're going to have 2 minus 2. Remember, we're still looking at this. So 2 minus 2 would be 0. And then -1 plus 3 would be +2. We'll graph that point, 0, 2. And that's my image of B. And then the last one would be C. We're going to take 2, subtract 2, which would give us 0, -4, add 3, which would give us -1. So 0, -1 would be right there. That would be C. And our shape would look like that. Now, are these two triangles congruent? If I'd drawn it correctly, you would have said yes. They are congruent because through this rigid motion, we have maintained size and shape. Now, what type of transformation is it? You'll notice that each vertices was moved the same distance. Basically, we slid the triangle over, which is translation. So for 5 and 6, you're going to draw the new image, which we should not have a problem on. That should be review. And then you're going to state, just like 1, 2, and 3, if there is congruence, and if there is congruence, what type of transformation is used to obtain the new figure. Okay, let's look at the next page. All right, these 8 through 13, you should be okay. Again, this is through this is a review of the last chapter. Looking at number 8 briefly, you'll notice these symbols mean congruence. That means we have two isosceles triangles. We have this triangle that has these angles congruent because of these segments congruent. So we would set up 3x plus 10 is equal to 5x minus 10, which then will get our value for x. But however, we have to find the value for y. Now remember, these segments are also congruent. That means these angles are congruent. I don't know what this angle is, but if I knew what this angle was, I could subtract it from 180 to find it, because we have a linear pair here. Now, if I found this angle, I can find it because if I know what the value for x is, once I do this algebra problem, I could plug it back in here, get a value for these two angles, add them up, subtract from 180, and I would get this angle right here, which then could lead me on, and 4y would be equal to whatever this angle was right here. Okay? Again, the whole these 6 problems are like Unit 6. What we worked on from the last unit, so I'll let you work on the rest of those. The last page, we should be able to do this. This was on the test. We struggled a little bit on this. I'll give you a couple formulas. 20 through 23 are similar to the previous page, but I'll give you a few of the formulas to make it a little bit easier for you. The midpoint formula is where we add the x's, divide by 2, add the y's, divide by 2. That's the midpoint formula. Distance formula. I'm going to zoom in because that one's going to take more writing. x2 minus x1 squared plus y2 minus y1 squared. Okay, so there's the distance formula. The slope formula, you remember that that is y2 minus y1 over x2 minus x1. And the slope intercept form, you have to put it in point slope first, which is y minus y1 equals my slope, which is what m is, times x minus x2. All right. Hopefully this helps on the assignment, and that's it.